All right, recording started. So I see a lot of people in the room today. So thank you very much for joining us for this exciting, very, I think, interesting tutorial. We have a lot to learn and we have an expert. We are very lucky to have Utsav Sadana today with us, who's, I think everyone knows, he's one of the main attendees, key attendees of our Stochastic Programming Seminar Series. So we really appreciate, Utsav, your participation and interesting questions for every seminar. And Utsav is currently an assistant professor in the Department of Computer Science and Operations Research at the University of Montreal in Canada. And he's also a member of Gerard and Gerald there. He earned his bachelor degrees at IIT Kanpur in material science and engineering. Also, he did a master's in economics. And later, he moved to HEC Montreal to do his PhD in management science. He finished in 2021. And then afterwards, he did a postdoc at McGill University for a couple of years. He also, during those times, he also visited actually University of Illinois at Urbana-Champaign for about a year. And his research, I think many of us familiar, especially based on what he's going to present today, but he also works on dynamic game theory, a lot of data-driven optimization, distribution optimization, all for better decision-making under uncertainty. The last but not the least, Utsav has contributed significantly to our last SPS newsletter, so we really appreciate that contribution as well. With that, the floor is yours, Utsav.
Thank you, Merve, and thanks, Giorgio, for inviting me to give this tutorial. And thanks, everyone, for joining. So today I will talk about contextual optimization. In recent years, contextual optimization has become a really popular area. And so what we did was, in around 1.5 years ago, we wrote a survey on contextual optimization. So this tutorial will be based on this survey, and most of the things that I will discuss are shaped by discussions with my co-authors, Abhilash, Eric, Alexandre, Emma, and Thibaut. Please feel free to stop me if you have any questions. As you all know, I am very fond of questions, so please don't hesitate to ask. So let's begin. Let's start with a stochastic optimization problem. You have a random variable y that affects the cost. What you want to do is you want to find a decision that minimizes this expected cost. If you knew the true distribution of y, you would solve this, you would minimize this expected cost over your decisions, and you will find the optimal decision. However, the true distribution is not known. What you have are data points, y1, y2, and yn. Based on these data points, you construct an estimate of your cost for any decision z. And this estimate is basically the empirical average of your cost. Now you plug this empirical average in a optimization solver, and you also plug in the constraints, you get a decision, z hat star. Now, this z hat star may be, in general, may be different from the optimal decision that you would have obtained if you knew the true distribution of y. Let's see an example. Suppose you are Zara and you want to decide how much quantity should you order. If you order more than the demand, which is y, you have to pay a storage cost. If you order less than the demand, you have to pay a shortage cost because the customers are disappointed. And the penalty for both these costs are given by these constants h and b. Now, a news vendor would solve this stochastic optimization problem and find the optimal z. If this expectation or the true distribution of y is not known, you would replace this expectation with the empirical average. We already know that the optimal solution for this problem is given by the critical quantile. So basically, if the distribution of demand is given here and b by b plus h is 0.9, then the optimal order quantity is given by the 90th percentile. So you can see here that the mass on the left-hand side of this dashed line is 90%. Now, suppose that you live in Montreal where it snows a lot. You may expect that the number of customers who will show in the store would be less if there is a snow. While if it is a sunny day, you would expect more customers. So basically, the distribution of the demand is to the left, which is given here in blue, if there is a snow, while if it is sunny, the demand distribution is given by this yellow. Now, you can also look at this through this CDF, the cumulative distribution function. You can see that the cumulative distribution function has shifted to the right if it is sunny, while it is shifted to the left if it is snowy. So you would want to order more when it is sunny, while if it is snowy, you want to order less, right? So basically, this information about the weather helps us to make better decisions. Instead of ordering 100, we would order around 109 when it is snowy, when it is sunny, right? So the whole area of contextual stochastic optimization tries to use this side information that is revealed before an action is taken and before the uncertainty is realized, and to make better decisions. And in this talk, I will discuss what are the different methods that are used to incorporate the side information to make better decisions. Before going into detail about the contextual stochastic optimization, let's look at some success stories of contextual stochastic optimization. There is this popular paper by Ban and Rudin, which is called the Big Data News Vendor. Here, the news vendor problem is as follows. You want to schedule nurses on a given day. If you have a lot of nurses, there is a large penalty for overstuffing. If the nurses are few, you have to pay again some cost. So it is just like the news vendor problem that we saw before. Here they see the features are the day of the week, time of the day, past demand observations. So basically, your historical data is the demand that you have seen and the features. Based on this, they determined how many nurses would be needed on a given day on the test data. And you can see that in blue, this is the actual or the required number of nurses on a given day in a UK hospital. And the red is the nurses that they predicted they would need. So you can see that the red curve is a reasonably good approximation of this blue curve. Another problem is a shortest path problem. So basically, this figure is taken from a paper by Alex Forel on explaining the decisions. So basically, what you have here on the right is the graph of Los Angeles downtown. You want to go from this point to this point, and depending on the time of the day, you can predict whether the green path is optimal or the blue path is optimal. Here they use as features the time, temperature, wind speed, rain, visibility, day, and month. However, if all these features you can keep as the same, and only the period of the day you can predict what is the optimal decision. Another problem is a portfolio optimization problem that we all are very familiar with. You want to basically solve a mean variance portfolio optimization problem. You want the mean of your returns of the stocks to be high, but you also want the variance to be low. So there is this famous paper by Butler and Keown about integrating predictions in optimization problems. So here they look at a commodities market with 24 commodities. They use as covariates as the 252-day return, which is basically the trend. And this carry you can think as the benefit or the cost of holding a commodity for a sufficiently long time. And they want to determine the optimal investment policy. Here, they use these features to predict the mean. Now, one can fit ordinary least squares model to the returns of the stocks based on these covariates, And what you will get as the equity growth is this curve in green. This is a sequential model where at the first stage, you predict the mean, and then you solve a mean variance portfolio optimization problem. However, in the integrated approach, you find your uh, predictions based on their performance on this portfolio optimization problem. And we will discuss these things in more detail now. So the classical setup of a contextual stochastic optimization problem is as follows. You have some side information. This information is revealed before you take an action. Now, what you want to do is you want to make a decision for any x which is feasible. So what you can do is you can solve this conditional stochastic optimization problem where the conditional distribution is given by P of y given x. So for a given x, you know the distribution of y, and you solve this problem for every x. Once you do this for every x, you know what is the policy that you should implement for any given x. Now you can see here that in the real world, we don't have all these features in our data set. Our data set could be a pair of x1, y1, x2, y2 until x and yn, right? Now, what we want to do is to learn a policy based on this data that can generalize to features which we have not seen in the data. So basically, what we want to do is to solve a policy optimization problem. Now, there is a nice connection between policy optimization and contextual stochastic optimization. So what you can do is you can find a policy that minimizes the expected cost over the joint distribution P of x and y. So here you get a policy for each x and y. Sorry, so you get a policy for each x. And this policy that you find, it's equivalent to finding for each x a policy by solving a contextual stochastic optimization problem. So policy optimization and contextual stochastic optimization are equivalent. And this enables you to basically solve this policy optimization problem and thereby get a policy for your contextual stochastic optimization problem. So this connection is given in this theorem 14.60, which is a popular theorem in the literature on contextual stochastic optimization. So in some of the discussion that I will do later on, I will denote this conditional expected cost with this operator H, which takes as input the decision Z and the conditional distribution of y given x. And the unconditional expected cost would be denoted by this capital H, which takes as input a policy and the joint distribution of x and y. Please feel free to stop me if you have any questions. So in our survey, what we do is we identify 3 different frameworks for learning policies from data. The first one is a decision rule optimization or a policy optimization. So you take as input x. Suppose you have learned a decision rule which is parameterized by theta, and you found that the optimal theta is theta hat. So what you do at the time of decision is that you plug this x into your policy, and this gives you your decision that you should make. You can also do a sequential learning and optimization approach where you first learn a prediction or a prediction model for your outcome, which is y. And then once you have learned this model, you use this model to make decisions. Similarly, you can also learn this a prediction model in the integrated learning and optimization approach based on the decision quality of your predictions. However, in both these cases, the decision pipeline that you will use is the same. So you will take as input an x. This x will be passed through your prediction model. Suppose the optimal prediction that you learned from your data was theta hat. You plug this f theta hat, which is the conditional distribution of y given x, and you plug it into an optimization solver. You solve your optimization problem and you get your decision. And in the remaining time, I will discuss how can we learn this pi theta hat, or basically this pi theta, how can we learn this f theta based on these three different learning paradigms. So the simplest case of a decision rule is a linear decision rule. You assume that your decisions are linear in the features, right? You can also assume that your decision rule is a neural network. You plug this X in your neural network and it gives you a decision. Here, your prediction model could be a normal distribution where the mean and the variance depend on the covariates. And you can fit a maximum using a maximum likelihood estimation, these theta and sigma to your data. You can, in fact, learn uncertainty sets and then use these uncertainty sets to make decisions based on your covariates. So these frameworks are quite general. In the literature, if you see, this decision rule optimization is also called policy optimization. The sequential learning and optimization is used quite a lot in the literature. There are two different kinds of frameworks. One is where you make a point prediction and use that point prediction to in an optimization problem. This is called predict then optimize or prediction focused learning. Another is estimate then optimize, where you first learn a conditional distribution from the data and then use this conditional distribution for an optimization problem. These integrated learning and optimization problems models have a lot of names. For instance, we all know this is smart predict then optimize, which enriched our understanding of these integrated learning and optimization models. Then there is this task-based learning models. There are end-to-end learning, optimization, and forecasting models, decision-aware learning, decision-focused learning. They all mean the same thing, which is that you are learning your prediction models based on their decision quality. So let's start with decision rule optimization and see how we can learn the theta, which is uh, the parameter for your decision rule based on data. So you start with some theta, you pass your covariate through this decision rule, you get your decision pi theta of xi. You evaluate the cost of pi theta xi on your data, which is yi. And the goal is to basically minimize this loss here. So you take the gradient of this cost here with respect to theta and you move in the direction which reduces the cost, right? Which is given just by your gradient of cost. So now the thing is, this policy optimization problem is an infinite dimensional problem. So what we need to do is we need to fix the class in which we search for our policy. In this famous paper by Ban and Rudin, they consider linear decision rules. So basically, your policy is linear in the features, which are these x's. So basically, you want to find a Q that minimizes this expected empirical cost, and they add this additional regularizer, which is dependent on the norm of Q, to basically get finite sample guarantees on the out of sample performance of the policies. If your problem is high dimensional, what you can do, what can happen is that you can overfit to the data. So this lambda here helps you to control the out of sample performance of your policies. However, there is a shortcoming of these linear decision rules, that they are asymptotically suboptimal in general, because even if you have infinite data, these linear policies may not approximate the nonlinear policies, right? And this leads to what we call as nonlinear decision rules. A simplest way to construct these nonlinear decision rules is to transform your features and now assume that your policy is linear in these transformed features. Another approach is to project or basically lift these features into a reproducing kernel Hilbert space. And on that space, you solve your policy optimization problem. This was done by Ban and Rudin, Baziermat and Dalaj, and Bersimas and Koduri. In Zhang and et al., what they do is they use piecewise affine decision rules, and they show that these piecewise affine decision rules can outperform models with policies in the reproducing kernel Hilbert space. Another approach, as you would have guessed, is to use neural networks to basically determine these decisions. However, these neural networks lack interpretability. Now, we like distributionally robust optimization. So what if instead of doing regularization, we use distributionally robust optimization? So here, what you want is to find a policy that performs well not only against the empirical distribution, but against all distributions which are at a distance r from this empirical distribution. Now, the way you measure the way they measure this distance in the paper by Shafizadeh Abadeh is using a Wasserstein ambiguity set. Now, if you restrict attention to linear policies and you solve this distributionally robust optimization problem, they show that it is equivalent to solving a regularized news vendor problem, or basically a regularized optimization problem. And now this penalty term also depends on the Lipschitz constant, as well as on the norm of Q. The main shortcoming of this decision rule optimization based approach is that it is very difficult for you to ensure that the constraints are always satisfied. This leads us to what is called the sequential learning and optimization approach, where by definition or by construction, the decisions are always the constraints are always satisfied. So you have this context X. You pass this context through your prediction model. You get your prediction f theta hat of X. You plug this prediction into your optimization problem. You write all the constraints. And now by construction here, you will satisfy the constraints. And now you will get your decision which satisfies the constraints of your problem. So this is the two-stage approach. Okay, I think Phoebe has a question.
Yeah, sorry, I'm sorry to interrupt. And sorry that my voice is gone. And hopefully you can still understand what I'm saying. So I didn't understand why you couldn't impose constraints on the policy file and thereby, optimize over this constrained policy space.
So you learn this policy pi of theta here.
Like if you did linear decision rules, couldn't you impose constraints on that linear decision rule?
So what you need is even whatever X arrives, for here you will impose in the data, you will impose these constraints on your policy. But for any feature that arrives which is not in your data set, again you need to project these you can project these basically these decisions on your space, but then this is not what you are doing at this step. This is completely different. You did not take into account while learning this policy Q transpose X all the decisions that you will have to make for all the X's that will arrive later on. So this is the challenge here, that you need to do it in a deployment phase.
Right.
While here in the deployment phase itself, you can impose these constraints on your decisions.
I see. I think that Rui Gao has something that extends.
Yes. So he has this way of extending policies to using. There is some notion of his that he can basically he uses Shapley values, I think, and using Shapley value he can project. He can extend these policies for all covariates, not just for covariates that are in your data set. However, I mean, the challenge is it's still complicated. I mean, the thing is you can do that. It is complicated. Here, it's natural to think, and that has been the criticism in the literature on of a linear decision rule or any kind of decision rule, that constraints are really difficult to satisfy for more general problems.
Got it. Okay,
Yeah.
thank you.
Thanks for your question. So now you want to learn this model f theta from data, right? So what you can do is you can minimize the estimation error between your model, which is model for the conditional density, and your empirical distribution. You would regularize as well because you want to basically not overfit to the data that you have seen. A classical approach is you will maximize the likelihood of observing your data under your model f theta, which is equivalent to saying that you will minimize the negative of the log likelihood. Uh, for nonlinear cost functions, you would want to basically learn this conditional density estimator, right? However, it is sufficient for you to learn just the mean from the data if your problem is linear in the uncertainty. And this is what most of the literature in contextual optimization focuses on. We call these models as expected value based models. So here, if you see, there is no uncertainty in the constraints, and you want to basically minimize the expected cost. Your cost is linear in y, which is your outcome, and your prediction is f theta, right? So now you can see that z does not depend on f theta, so you can push this z outside. And now you are left with expectation of y. And what is this? This is just the mean under your model evaluated at x. So the only thing that you care about is the mean in these models. This is the same as a parameter estimation problem where you have reduced this stochastic optimization problem to somewhat a parameter estimation problem and then optimizing, right? So, and we know already how to estimate the mean from the data. We can use linear regression. So instead, there is no need for you to learn this whole distribution in linear optimization problem. You can just learn the mean. Now, in stochastic optimization problem, we like to do SAA, right? So what you can do is for every covariate that arrives, you want to solve this stochastic optimization problem. You want to find a Z that minimizes this conditional expectation. Now the goal is how to construct this f theta, right? So what is done in the literature is to assume that this f theta is a discrete conditional distribution, and in there are different approaches. The first one is this residual based approach, which the idea of which I think occurs in Deng and Sein in 2017, and recently the paper by Kanan and others was published in 2025. So basically what you do here is you take your data, you basically fit a regression model, you get your mean, you compute what are the errors your model is making on the data. Now, instead of making point predictions only with your mean, you construct the whole distribution by putting a uniform support on these errors and translating all these errors by g theta of x. Okay, so this is how they construct a data-driven noise model around the trend or the mean, and they use this f theta x in their uh, conditional stochastic optimization problem to make decisions for every x that arrives over time, right? Another model is the weighted SAA model. Here what you do is you say that the instead of putting a uniform support on your scenarios, I will weigh each of these scenarios with the weight function that depends on the covariate. So here the idea is, if you see in your data and the covariates are close to this new covariate, then the data points which are close to this covariate are more useful to make decisions, right? So basically the idea is you you construct these weights here using k nearest neighbor. So you look at your data, find the k closest covariates to this x, drop all the other covariates and put equal weight on the covariates which are closest to this x. Now, Another approach is this kernel density estimation. Instead of dropping dropping the covariates, what you do is you put weights on your covariates in inversely proportional to the distance of the covariates from your x, right? So the weight of xi is decreasing exponentially with distance from x. Now, what you can also do is you can do something of this supervised learning approach. You can learn a decision tree. Now, once you learn this decision tree, you can do it for classification, for regression. You will have branches and leaves. Now, what you do is you look at your data set and you check which of the data points in your data set have covariates in the same leaf as your new covariate x. You drop all the other covariates, all the other data points, and you put a uniform distribution on these covariates which are in the same leaf as your x. You can do something more much better by considering several decision trees, and then you take the average of the weights of these decision trees and use these new weights to make decisions about every covariate x. Now, let's see a benchmarking study on a news vendor problem that was conducted by Butler and others. So here they use 4 data sets, this bakery data set, M5, restaurant, SID. They consider 5 variations of the problem parameters for every data set. Okay. Now on the y-axis, you see the percentage of instances for which a model of a given color outperformed other models. So you can see here that for random forest, for 60% of the instances when the problem parameter setting was BC, the best model was random forest. So you can see that the blue color appears predominantly, and across data sets, random forest does remarkably well. The next model that performs really good is linear decision rules, where you can see the color green appearing predominantly um, in this figure, right? Now, you can see that deep learning based model don't perform really good, right? And similarly, kernel based models or in k-nearest neighbor sometimes performs good. You can see some appearance of this purple color and so on. And decision trees don't work well in practice in these for these data sets. Okay, so these sequential models are really interesting, right? You can train your model by doing maximum likelihood estimation, and then you can plug these models into your optimization problem and make decisions. In fact, what we know is that for nonlinear optimization problems, sequential models stochastically dominate integrated models. Integrated models are models where you learn the predictions based on the decision quality. So basically, if you know that your hypothesis class covers the true distribution. For instance, in the news vendor problem, you know exactly, suppose that the true distribution is gamma distribution for your demand, and you also see that your hypothesis class has this gamma distribution. Then you can show that asymptotically sequential models will perform better than uh, integrated models. So there is a result in this paper by Al Maktoub and others. Now, it is unreasonable to expect that we always know what is the hypothesis class which it is unreasonable to expect that our hypothesis class will cover the true distribution. So this is what we call as the model misspecification setting, meaning that the hypothesis class does not have the true distribution. In this case, asymptotically integrated models outperform sequential models. In fact, if you have a finite data, there are a lot of papers where it is shown that integrated models outperform sequential models. in the finite sample settings. And that's what has motivated this integrated model learning and optimization, which I will now discuss. So basically, the idea is as follows. You want to learn your prediction model based on the decision. So you take your context, you put it through your prediction model. Now you will get a prediction of your y. This prediction is f theta xi. If you cared only about your statistical accuracy of your model, you will learn this f theta xi based on how well this f theta xi fits to the data of xi and yi, right? Now, what we want is to learn prediction models which lead to better decisions. So what you do is you plug this prediction model into your optimization problem. Now, once you plug this, you get a decision. Note here that the decision that you are getting is under your model, right? Even if you plug this decision in your cost function, what you get is a cost under your prediction model. Now, what we care about is the true cost of our decision, not on the cost that is under our model. So what you do is you evaluate the cost of your decision on the data. The data is yi, right? This is the actual scenario that we care about. This is where we want to make good decisions. Ideally, we want to make the good decisions on the out of sample data, but for now, assume that this is a good representation for us to make better decisions, okay? So you evaluate your decisions on the task, right? This is the task. This is the model, right? Now, the question is how to minimize this cost, right? So what you would do is you want to learn this theta that minimizes this cost. So you take the gradient of this cost with respect to theta, and then you move in the direction which improves your cost. Note here, to take the gradient of this cost with respect to theta, you need to take the gradient of this z star with respect to theta. Now, this z star here is coming from this argmin operation. So it is not differentiable in general, right? This argmin operation is not differentiable. And we will see how to basically take gradients of this z star with respect to theta very shortly. So the first paper to learn decisions based on this task-aware model was by Yoshua Bengio. They used a fixed decision rule and they considered point predictors. That is, they were looking at mean estimation instead of conditional density estimation. Later on, Donti and others learned conditional density estimators using this training pipeline. And very recently, Shen Reddy and Delage learned task-aware uncertainty sets by modifying this task loss and this training pipeline that you are seeing here. And they learn this uncertainty sets based on the actual decision quality. So let's see some motivation for doing this task-aware learning, okay? So the idea exists in this paper by Al Maktoub and Grigas, and this figure is adapted from their paper. So basically, suppose you want to maximize your reward, okay? And your reward is linear in your decisions. Sorry, the reward is linear in your uncertain outcome y. So basically, what you care about is the expectation of y given x. If you could tell me what is the exact expectation of y given x, that is the mean, I know what is the optimal decision, right? Suppose you make a prediction which is expectation of y given x, which is you make a prediction which is exactly equal to this value, right? So you know that the decision is z star, right? Now suppose you make an error of epsilon 2, and now you check what is the optimal decision. Again, the optimal decision is z star. Now suppose you make an error epsilon 1 on this side. Now the optimal decision is this. But this decision is suboptimal because the true value of the mean is expectation of y given x and not expectation of y given x plus epsilon, right? So this decision will give worse performance when under the true model, right? So basically what matters is not the magnitude. Even though epsilon 1 is less than this epsilon 2, the direction in which you make the errors matters, because if you make the errors in the wrong direction, you can have suboptimal performance. However, these sequential learning and optimization models don't see the errors at the time of decision. What they care about is the errors based on the statistical accuracy, right? They have no way to distinguish between epsilon 1 and epsilon 2. So this is the idea behind behind smart predict and optimize, that you want to basically learn predictions which lead to better decisions. Now I told you that differentiating through the argmin operation, you cannot differentiate through argmin operation because it is not differentiable in general. But what you can do is these use these different models. So the first model is, suppose you can write your optimization problem as an iterative solver. Okay, you have an iterative solver that gives you the solution of your optimization problem. You can put this iterative you can put these iterative steps on the computational graph of your problem, and now you can differentiate through the computational graph. In some cases, you can even write your optimization problem as a fixed point equation and now differentiate through this fixed point equation using implicit differentiation. So now what the thing is this, suppose your problem is a convex optimization problem, okay? Now what you can do is you can write the KKT conditions of your problem, okay? The KKT conditions, suppose, are represented by this equation f of y hat. Y hat is your prediction, z is your decision. And these f y hat z is 0. This is your, suppose, your KKT conditions, okay? Now, you can, under certain conditions, do implicit differentiation. And now you can compute the gradient of your z star, which is your decision with respect to y hat. Here, this is a Jacobian matrix. In fact, you don't need to write all these steps. There are libraries like TorchOpt, CVX, PyLayer, PyEPO, JXOpt, which can do it for you. You don't need to do these steps, right? So everything looks very good. If you want to do convex optimization, you can do this, and you will find the optimals. You can find the optimal solutions for your problem. You can take gradients. The problem here is that at each step, you see here, at each step of your gradient descent method, you have to write these KKT conditions. Then you have to take gradients of these KKT conditions and then pass these gradients to your prediction model. And again, you have to do this. So this is really time consuming, okay? We don't want to do this, okay? Another thing that we don't want to, another challenge here is that if this matrix here is non-invertible and your problem is non-smooth, these gradient-based methods can get stuck in a limit cycle. So basically your gradient methods may not converge. And this was proven by Bolt and others in 2021 through an illustration. We have a discussion about these models in our survey. You can look into it. So now what we want is not do implicit differentiation. We don't want to do implicit differentiation. Can we do something else? That's the goal. Can we construct some surrogate models that circumvent the need to use implicit differentiation, implicit function theorem? So these models are that we can, now I need to rush, I think. So what we can do is we can construct models based on some regret, which can which don't require you to use implicit differentiation. So you see here this policy pi theta that you learned from your data, learned from your model g theta, which is your prediction. You evaluate the cost of this policy on your scenario y. You compare it to the true cost of your optimal decision, which is z star. And this is basically the regret that you will suffer. Now you can see that this term here does not depend on your decision. So what you are left with, you can just drop this term, and what you are left with the loss function for a ILO model, the integrated learning and optimization model without regret. So regret minimization and integrated learning and optimization have the same set of minimizers here, okay? However, the problem is that this pi theta that you get from minimizing this cost, it may not be unique. There could be many decisions that are optimal against your prediction. So what El Maktoub and Grigas propose is a smart predict then optimize model, which is basically a pessimistic bi-level model, where in the first stage, or basically what you do is you choose your theta to minimize the worst case regret, where the regret is over all decisions that are optimal under your model g theta. So what they get is this LSPO loss function. Now what happens is that this LSPO loss is not differentiable. So they replace this LSPO loss, which is just basically a worst case regret model, with a convex upper bound on this loss. Now the nice thing about this loss LSPO plus is that it is differentiable and it has a closed form subgradient. Now we like closed form subgradients because we can directly use this in our subgradient method to update our theta, which is our prediction model. You can do something based on imitation learning. What you can do is for each x and y, you decide what is your optimal decision. So you solve an optimization problem for every x comma y. You get your best hindsight decision based on the data. You create an augmented data set of xi, yi, and zi star. This zi star is your optimal decision. And now we call imitation loss as the expectation of the distance between your policy pi theta and z star. Okay. Now, depending on what distance you choose here, you can get different models. Okay. For a particular choice of distance, which is this, you get your H at imitation. Your imitation loss is the same as the regret loss. But still, it suffers from the same issues that regret loss suffers, that the gradients may not be existing, or you can have jumps in your optimal decision. So this H imitation is also not differentiable in theta if you choose this kind of a distance. Okay, we will see what you can do to make this differentiable. So let's look at what is called as differentiable perturbed optimizer. So here, the problem was that this argmin operation was not differentiable. This, for a given theta, the decision was not differentiable. So what they do here in this paper is very smart. They they inject some noise into g theta. Okay. For every noise that you inject, your decision will keep moving on this polyhedron, right? For every noise level eta, you will move in this polyhedron. And now what they do is they take the average decision. So they take the expectation over noise of these decisions that you are implementing. Now this Z that you got, which is an averaged Z, which is the average decision, this is smooth and differentiable with respect to theta. You can plug this Z into your loss function and you can compute the gradients using Monte Carlo simulations. You can do something even more smarter. In your imitation learning based loss, you can replace the distance with a Bregman divergence. And then you can show that your imitation loss is just the expectation of your Fenchel-Young loss. Now this loss is interesting because the gradient of this loss function is just available to you analytically. It's just the distance between the optimal decision under x and y minus the optimal Z that you constructed, or basically the average Z that you constructed by injecting noise into your predictions. So basically what you can do is use these gradients and keep updating your predictions. And this is analytically available to you. You can do something more general. You can say that the noise is Gumbel, then you will get a distribution of Z of epsilon, which is the averaged Z epsilon, which is given here. And now you can learn the optimal theta using maximum likelihood estimation. In fact, in Monkey's paper, what she does is she replaces this whole optimizer itself, this zx of theta, with a neural network. And now you ensure that your z is differentiable. So there are many things that you can do with this z, with this basically this prediction model, this training pipeline, to basically eliminate the need to do this step. You don't want to do this. It's really time consuming. So let me just wrap up by showing that these integrated models have performed well across different problems. For instance, you can see here that integrated models lead to lower cost in a news vendor problem. Another paper by Chung and others showed that you can minimize the unmet demand for medicines in a real world setting in Sierra Leone is by using this decision aware loss, you can reduce the unmet demand as compared to if you use a classical OLS based model. This is another news vendor kind of a problem where again they show that integrated learning and optimization models perform really well. So finally, I can discuss in very briefly about what are the current active research directions. The first one is how to construct surrogate models which circumvent the need to use implicit differentiation. Most of the models that I discussed, almost all the models that I discussed, they have no uncertainty in the constraints, right? There is some active research in the last 1 year on including uncertainty in the constraints, but I feel that this problem is more or less open to address. Another issue is this data-dependent uncertainty, how to include contextual information and construct decisions when you have decision-dependent uncertainty. Another active area of research is to develop finite sample guarantees on the performance of ILO models for nonlinear problems. Monkey has some results on this problem, but where the support of your uncertainty is discrete, and the labels can be costly to obtain, and you also would like to have some risk and robustness aware contextual optimization. These are some of the active research directions. Finally, I can conclude by saying that contextual optimization is a really interesting field, especially for me. I really like it. And this can enable you to identify data-driven decisions that can exploit the most recently available information. There are 3 types of approaches. You can use decision rule optimization, sequential learning and optimization, or integrated learning and optimization. And you have 3 or basically 4 different performance measures. First is you can look at the statistical accuracy of your prediction model. You can look at the regret of your model. You can also look at the task-based cost of your model on the task. Or you can look at this imitation-based learning approach to learn predictions. Thank you very much for your attention. And sorry for being out over time.